Energy band structure of conductor. In the conductor, this Fermi energy level lies within the conduction band. In case of the semiconductor, it is in the middle of energy gap, but in case of the conductor, this energy level is within the conduction band. So what happens in this case? Electrons in the conduction band easily jumps to free energy levels. They easily jumps to free energy level. They then pick up the speed and drift in the direction of electric field and drift in direction of electric field. This is how they conduct electricity. This is what happens in conductor. Let's see the energy band structure of conductor at 0 Kelvin. Energy band structure of conductor at 0 Kelvin, at absolute 0 temperature. The temperature is 0 Kelvin. So here I am showing you the diagram of this conduction band. This is conduction band of conductor, and as you can see, at absolute 0 temperature, this conduction band is filled up to certain energy level, up to this energy level, which is called Fermi energy level. In this case, conduction band is filled up to certain energy level. EF, called Fermi energy level. As you can see, this is the Fermi energy level, which is marked by EF. There are large energy levels vacant above EF. Okay, as you can see in the diagram, there are large vacant energy levels above EF. Large energy levels above EF are vacant. So we can define this Fermi energy level as highest field energy level in conductor at 0 Kelvin. This Fermi energy level EF we can define as highest field energy level in conductor at 0 Kelvin. Fermi energy level is highest field energy level in conductor at 0 Kelvin. This is called the Fermi energy level. Then what would be the Fermi energy? So the Fermi energy we can define as maximum energy that an electron can have in conductor at 0 Kelvin. This EF energy level has maximum energy which is occupied by electron. And so the Fermi energy is maximum energy that an electron can have in conductor at 0 Kelvin. So we define both Fermi energy level and Fermi energy for a conductor at 0 Kelvin. Fermi energy level is highest field energy level in conductor at 0 Kelvin. So we can see in this diagram, this is the highest field energy level, which we are calling Fermi energy level. And that energy level, electrons are equals to the Fermi energy. So Fermi energy is maximum energy that an electron can have in conductor at 0 Kelvin. So that's how we define Fermi energy level and Fermi energy. Then let's see the Fermi Dirac distribution function for conductor at 0 Kelvin. Fermi Dirac distribution function. Let us consider energy level above EF. Consider in this case energy level E above EF. Any energy level which is above EF. As you can see in this case, all energy levels which are above EF are vacant. So what would be Fermi Dirac distribution function for those levels? Let us find out. So in this case, we have considered energy level E above EF, and that's why E minus EF, the difference between them. In the diagram, the E can be any energy level above EF, and this is Fermi energy. So if you take the difference E minus EF, that difference is positive. Then according to the probability function, that is a Fermi function, f of E is equals to 1 upon 1 plus e raised to E minus EF upon kT. But in this case, E minus EF is positive and kT is 0. In this case, kT equals to 0 because we are considering the conductor at temperature T equals to 0, so the product kT is 0. So this becomes then 1 upon 1 plus e raised to some positive quantity divided by 0. So that would be 1 upon 1 plus e raised to positive infinity, which is nothing but e raised to infinity. And e raised to infinity is infinity. So 1 by infinity is equals to 0. So f of e is equals to 0 for all energy levels above EF. So all energy levels above EF are vacant. It showed that all energy levels above EF are vacant. Then let's consider energy level below EF. See in the diagram. This is EF over here. Now we are considering any energy level which is below EF. Let's see if those energy levels are occupied or vacant using the Fermi Dirac distribution function. So this energy level E is below EF. So E minus EF. EF is the highest energy. Below EF, this E is smaller. So E minus EF would be negative. E minus EF is negative. Then Fermi function f of E is equals to 1 upon 1 plus e raised to E minus EF upon kT. Again in this case, kT is equals to 0 and E minus EF is negative. E minus EF is negative. And therefore, this is equals to 1 upon f of E equals to 1 upon 1 plus e raised to minus infinity. And e raised to minus infinity is 0. So 1 upon 1 plus 0, and this is equals to 1. So probability function we got 1. F of E is equals to 1. When you get it 1, it means that the particular state at energy E is occupied by the electron in case of conductor. So F of E is equals to 1. It means that all energy levels below EF, which are below EF, are filled because their probability function we got 1. So all these energy levels below EF are filled. Then let's see what happens at EF. Third case, consider E equals to EF. We are considering the same energy level, EF. So let's see what the probability function for EF we get. So E equals to EF, so E minus EF is equals to 0. And so Fermi function f of E is equals to 1 upon 1 plus e raised to E minus EF upon kT, and in this case 1 upon 1 plus e raised to 0 by 0. And so this is indeterminate. We can't find it. It means that f of E at E equals to EF can have f of E equals to 0 to 1. F of E at E equals to EF, this can be from 0 to 1. It can have any values between 0 to 1. So this was for conductor at 0 Kelvin. Then let's see energy band structure of conductor at higher temperature. Energy band structure of conductor at T greater than 0 Kelvin. So at some temperature. What happens if the temperature is not 0 Kelvin? So at temperature above 0 Kelvin, what happens in this case? What will happen is electrons near the Fermi level. Let me show you in the diagram. So the temperature is not 0. It means that the thermal energy is equals to kT. We are providing thermal energy kT. So that energy will be absorbed by the electrons which are below EF in the range kT, and they will be excited above EF in the range kT. So at temperature above 0 Kelvin, electrons near Fermi energy level. Near Fermi energy level absorb thermal energy. How much thermal energy they will absorb? They will absorb thermal energy kT. T is the temperature, K is the Boltzmann constant, and excited to higher energy level. Excited into higher energy level. Now, which electrons will absorb this energy kT? Can any electrons in the conduction band absorb that energy kT? The answer is no. Only electrons in the range kT below EF absorb thermal energy. And excited to energy levels in the range kT above EF. Let me show this in the diagram. This is the Fermi energy level here in the diagram. This is the Fermi energy level. Now, those electrons, we are supplying the thermal energy kT. Temperature is increased. When the temperature is increased by T, it means thermal energy equals to kT. K is the Boltzmann constant. So this thermal energy will be absorbed by the electrons which are below here, which are below EF in the range kT. Suppose this is the range kT. So only those electrons which are below EF in the range kT, they will absorb this thermal energy. Electrons at this level will not absorb the thermal energy. Only those electrons which are below EF in the range kT absorb the thermal energy, and they are excited into higher energy level above EF again in the range kT. So I have shown here some of the electrons are excited from lower energy level in the range kT, and they have entered into higher energy levels. So because of this, what happens? Because of this, energy levels below EF in range KT are partially depleted. Are partially deflated and energy levels above EF in range KT are partially filled. When temperature was zero, all the energy levels above EF were vacant, and all energy levels or all energy states below EF were filled. But now, when the temperature is increased, so in the range KT, some of energy states are not occupied, and some of energy states above EF are occupied. So energy levels below EF are partially depleted and energy level above EF are partially filled. So because of that, probability of finding electrons below EF, earlier it was 1 when the temperature was uh, 0, then all the energy levels below EF were filled. Now temperature is increased. So probability of finding electrons below EF in range KT becomes less than 1. Earlier it was 1, now it would be less than 1. And probability of finding electrons above EF in range KT become more than 0. When temperature was 0, all energy levels above EF were vacant. That is, the probability was 0. But now, at temperature T more than 0 Kelvin, the probability of finding electrons above EF in the range KT become more than 0, or you can say greater than 0. Then what would be probability at E equals to E1? Or let me write probability at probability of finding electrons at E is equals to EF. When the temperature was 0, probability of finding electrons at E equals to EF was indeterminate. It can have any value between 0 to 1. Now we are studying what if the temperature is more than 0 Kelvin. Then what would be the probability of finding electrons at E equals to EF? Let us find that. It means that E minus EF is 0. So probability function, Fermi function is equals to 1 upon 1 plus E raised to E minus EF upon KT. Now kT is not 0. KT is not 0. Therefore, 1 upon 1 plus e raised to, but e minus ef is 0. E is equals to ef. So e minus ef is 0. So 0 by kT. So this 0 by kT is nothing but e raised to 0 by kT is 1. So 1 plus 1. And that's why we get half. So f of e, okay, f of e at e equals to ef is equals to half. Probability of finding electron is half. Then let us define the Fermi level. We already defined the Fermi level for conductor at 0 Kelvin. Now we are going to define here Fermi level for conductor at temperature greater than 0 Kelvin. So this Fermi energy level is the energy level at which the probability of finding electron is half. So Fermi energy level is energy level at which the probability of finding electron is half. In conductor at T greater than 0 Kelvin. So that's how we can define the Fermi energy level. For conductor at temperature T is greater than 0 Kelvin. We have defined these Fermi energy levels in early just now for conductor at T equals to 0 Kelvin, and that is highest field energy level of a conductor at T equals to 0 Kelvin. So that's how we define the Fermi energy level. Then what is the Fermi energy? Let us define Fermi energy. The Fermi energy, you can say now, see the Fermi energy. This is the Fermi energy level and this is the Fermi energy. So all the electrons, you know what happens in the range kT below EF and in the range kT above EF. These energy levels are partially filled. Below EF in the range kT, above EF in the range kT. These energy levels are partially filled. So all the electrons in the range kT above and below EF participate in the conduction process. Then we can define this Fermi energy as average energy possessed by electrons which participate in conduction process. For conductor at T greater than 0 Kelvin.